Hey, Christina, feel free to ask any questions if you have any, or wait for everybody else. Hey, about time. Hey, Michael, feel free to ask me any questions if you have any at this time. Huh. Oh, man. Still got about 2 more minutes. Feel free to ask me any questions. I'm just doing some last minute stuff. All right, got another one in. All right, it's 5:20. So anybody have any last minute questions before we get started up? I've asked everybody that was already here earlier, but now Ethan's here. We've got more students coming in, of course. But it's time to start. The last thing that I hadn't really done that matters in chapter 30 was addressing LRC circuits. That's circuits that have an inductor, a resistor, and a capacitor. And of course, if you have some part of it, these results from this differential equation uh, turn out to be basically the same differential equation that we had for a damped harmonic oscillator. So that part's not that big a deal. You can just look back in chapter 14 and see exactly what that is. But the main thing is there's some conclusions that we make that allow us to make phasor diagrams and that sort of stuff. So I really need to show you basically what the results are for that, which I'm pretty sure I didn't show you already. Let me double check real quick. The last time I had 242, there it was. Yeah, actually, I did do that. Okay, so I've already given you the part where it's this solution of the differential equation that that applies to basically a circuit with a resistor, or excuse me, with a capacitor that's initially charged up in series with a resistor, in series with a inductor. And from that, we got that Q of t equals Q0 e to the negative r over 2L times t times cosine omega prime t plus phi. And I even showed you what the initial condition or what the conditions were that would make the various underdamped, overdamped, and critically damped cases. So we did already do that. So the main thing is I need to show you what happens when we actually apply a source. So we've seen that basically you can have sort of a current that goes into the circuit and it sort of decays, and that's the case that's called critically damped, basically. Then there's a overdamped where it just goes down like that, and then there's underdamped, or actually underdamped is the one that goes like this and wiggles a little bit. But either way, it's the main thing is you know that because of there being no power source, the resistance is slowly eating away the energy, and there's some wasted in general for the wire resistance, as well as just part of the stuff from the inductor and the capacitor, because they have resistances as well. So all that's wasting energy, so eventually it'll die. But if you connect it with a DC, I mean with an AC source, then you can actually get some pretty neat results. And what I'm going to do is show you how we deal with that, and then how we deal with avoiding that nasty differential equation by introducing phasors. And I tell my students that we do this with electronics technicians, partly because it's a lot easier, but it's also because it's a lot easier for us. So it's not just because the electronic technicians, quote unquote, can't do it. I mean, obviously some of them can, some of them can't, just like some physicists can and some physicists can't, and so on and so forth. But the main thing is the phasor diagram makes life a lot easier. So I'm going to try to explain that to you. So first off, I'm going to draw a circuit with just a AC power source that has a current as a function of time. And I'm going to connect it in series with a resistor and then back to the AC power source and let you see how the voltage and the current are related. Then I'm going to do the same thing for an inductor. Then I'll do the same thing for a capacitor. And you're going to determine a couple things that are very important, specifically reactance and lagging and being ahead, current versus voltage, that sort of thing. So in fact, I've hinted to you that we get the phrase Eli the Iceman, and that's really what Eli the Iceman is about. Eli suggests that the electromotive force is ahead of the current, and the electromotive force, of course, means voltage, is ahead of the current in an inductor. That's why it's ELI. And similarly, ice, its current is before the electromotive force in a capacitor. So anyways, we'll show you why that's the case right now. So I'm going to start off by sharing the screen. I'm sharing the screen. Looks like everything's working. So I'll first talk about a resistor. So I'm just imagining a circuit with an AC source, and the AC source would be drawn like that. And then a wire comes out, runs to a resistor R. And I, for an AC circuit, could be called I0 times cosine omega t. And I0, of course, would be the peak voltage, or excuse me, in this case, the peak current. And of course, if you want to know the IRMS, you take that peak current and divide it by square root of 2, and you get IRMS. But the main thing is we know that. We also know that Ohm's law applies, and Ohm's law says that V is equal to I times R. So V, for this particular case, is just going to be I0 times R times cosine omega t. So in this particular case, you can actually graph the voltage and current on one graph and see something special. Specifically, this is time. And up here, I'm going to say this is voltage and current. So first off, I'm going to do the current, which I'm going to do in blue. And the current, of course, obeys the cosine function. So we're going to say I0 is this high. And what that's going to do is we're going to go down, hit here, hit here, hit up there, go down, hit here, hit up there, like that. That's the actual current as a function of time. It just looks like a cosine graph, so on and so forth. Now, if you realize looking at the voltage, the only difference is we multiply it by R. So now what I'm going to do is say this quantity is I0 times R. And you can see, in fact, the exact same thing happens, only now it goes here, and then it goes here, 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 like that. So you can see they're completely in phase. The peak of the voltage is at the exact same instant as the current peaks, and the trough is exactly the same time as the current troughs, and the zero line hits at exactly the same time as well. And that's what resistors do. So they're all in phase, is what we'd say about that. Now, what we're going to look at is the inductor. So in the case of the inductor, okay, we still have an AC source, only now the wire is going to carry the current. Oops. The wire is going to carry the current. And then come back here. This is an inductance L. Again, I is equal to I0 times cosine omega t. But in this case, V is equal to L di dt. So what we have to do is write the I0 out in front, because that's just a constant, and then times L, which is also a constant, but that's in front of the derivative anyways. But now we're going to take the derivative of cosine, and when we do that, we're going to get the derivative of cosine is negative sine. So I will put, actually, let me give myself a little more space. So I'm going to put a negative here, then I'm going to put the I0, and I'm going to leave a space for something else. And then I'm going to say, of course, the derivative of cosine is negative sine. So all I have to write here is sine omega t. But then according to the chain rule, I have to now take the derivative of omega t with respect to t. So that's going to give me an omega right here. Now, if you look at a trig identity, for instance, for cosine of omega t, I actually know where this is going to be. So if I wanted to, for instance, say, what is the cosine of omega t plus pi over 2, I know the identity for that is basically cosine A or cosine omega t. Somebody just came in. Get that. Cosine omega t times cosine pi over 2. And then minus sine omega t sine of pi over 2. Okay. Now, in this case, cosine of pi over 2 is 0. We can see that right here. Okay, so that part is 0. However, on this part, we know that the sine of pi over 2 is in fact 1. So this is just the same thing as negative sine of omega t, which, guess what? It seems that we actually happen to have a negative sine of omega t, because there's the negative sine and there's the omega t. So I can now say that I is equal to I0 cosine omega t, and V is actually I0 times omega L times cosine of omega t minus, or excuse me, plus pi over 2. Okay, so this shows what I was saying earlier, which is Eli. So the current lags behind the voltage. Well, actually, I don't want to write voltage in that small of an area. Oops, don't want to do that either. Behind the voltage by 90 degrees. So that's what that's actually saying. And we see that right here because that's 90 degrees. And you see that the voltage is actually ahead. In fact, if you wanted to graph that, we could do, let's say from here to here. So what I'm going to do now is I am going to make the current graph. So I'll say current will be in blue. And then the voltage will be in V. And what I'm going to do for the current is I'm going to say the current is right about here. In other words, that's its amplitude, about 1.5 blocks. And I'm going to draw it as cosine. So that means it's going to come down here, hit there, hit here. Like that. And this right here, of course, is just I0. But the voltage, however, we are going to call this V0 is equal to I0 times XL. And this XL is defined as the inductive reactance. Okay. It has units of ohms. So for instance, X sub L has units of ohms. And it's like resistance, only it is related to omega. As you can see, in fact, omega times L is the inductive reactance. So now I'm going to say up here is V0. So that's about 3/4 of the way up the third one. So I'm going to draw this little line to specify my amplitude. And of course, this was the same thing as negative sine, which also is like just starting at this part of cosine where I just drew that red dot. So that's really what we're looking at. So I will start with that and basically make the negative sign. So the negative sign would come all the way down here and all the way up here and all the way up here, all the way down here.
I have a question.
Yes. Oops, this one.
Is
Yes.
that Eli? Is that what it says?
Yeah, Eli.
Is that like an acronym?
Yes, an acronym, Eli the Iceman. So the acronym is Eli the Ice Man. That's what we use to remember it. And you can see that current is before voltage. That's what the E means, is voltage. So current is before voltage in a capacitor, but voltage is before current in a in an inductor. And this is actually showing you exactly why that is. You can see, in fact, that basically this plus pi over 2 means the voltage is actually ahead. So the voltage is actually jumping to where that red dot is that I just accidentally erased. It's jumping to that part of the current curve, if you will. So it's literally ahead by a quarter cycle. And that's what this plus pi over 2 means. Not only that, because of the similarity between V equals IR, which is Ohm's law, we can refer to I0 times omega L as being just like Ohm's law, only in place of I0R, we make I0 times XL, and XL will be omega times L. So you can see as omega, the angular frequency is actually 2 pi times the number of hertz, for instance. That number is directly proportional to omega. So as omega goes to infinitely large, in other words, really high frequency, then the inductor will actually act like a break in the circuit, because it's going to become an infinite amount of resistance. However, you'll see later when we do the same thing for a capacitor, which is our next step, we'll get a capacitive reactance called X sub C, and that's going to behave differently. And that's also going to cause us to find the ICE part, the ICE part, instead of the Eli part. So any questions on that? That was a good question, by the way. I'm glad you asked me.
No.
Anybody else have a question? I heard somebody say something. Oh, that was you again. All right, well, let's go ahead and look now at what's the capacitor going to do. Now, the capacitor is a little more complicated because unlike the last one where we could just take a derivative, this one we actually got to do an integral. So I'm going to say capacitor. Okay, for a capacitor, what I'm going to imagine is, again, a little AC circuit. So basically an AC power source, and then a capacitor of capacitance C, and that. And we know, of course, that C is equal to Q over V. So that means that V is equal to Q over C. We know that I is actually equal to I0 cosine omega t. And we also know that I is equal to dq dt. So we're going to have to use that. So it turns out that Q is going to be equal to the integral of dq from 0 to Q of, now the other part. So basically we're treating this little part right here like a differential equation, a separable differential equation. So I'm multiplying the dt times the I, which is I0 cosine omega t. So now I'm going to say the integral of I0 cosine omega t dt. Now, in this case, one way you can look at this is a simple substitution. We're going to let u replace omega t, then du would be omega dt, or dt would be du over omega. So I'm automatically going to get that q is equal to I0 over omega times the integral of cosine u du. And of course, the derivative of sine is cosine. So the integral of cosine is actual sine. So this is actually going to give me I0, and I'm writing it a different way for a reason here. You'll see in a second. I0 times 1 over omega times the sine of omega t. So that's what the actual charge is. And of course, that means the voltage, which is Q over C, is going to be I0 times 1 over omega C times, now here's the neat part. It turns out that sine of omega t is the same thing as cosine of 90 minus omega t, but cosine is in fact an even function, so that's the same thing as cosine omega t minus 90 degrees. So now we're going to say that I is equal to I0 cosine omega t, and V is equal to V0 times cosine omega t minus pi over 2, which, by the way, is also equal to I0 times 1 over omega c times cosine omega t minus pi over 2. So you can see by parallel, V equals IR implies V is equal to I0 XC. And of course, XC is defined as 1 over omega C. So I fit that all in there. Let me write it on the other page. What it means is we now have I is equal to I0 cosine omega t, and V is equal to V0 cosine omega t minus pi over 2, which equals, actually, I don't like the way that turned out. Let me fix that. Okay. Now this time we're going to say it's I0 times X sub C, which is times cosine omega t minus pi over 2. And X sub C will be defined as 1 over omega c. So in this case, the limit as omega approaches infinity of 1 over omega c equals 0. So in fact, this thing has 0 resistance as the frequency becomes infinite. So implies 0 resistance as frequency approaches infinity. And you can also realize that this is the same thing as sine. So if you graphed them, one would look like sine, the other one would look like cosine. But now we see why we have the ice portion, because clearly the voltage is trailing the current by a pi over 2. There's a couple of different ways of saying it. All right. So that's basically what all this was about, is one, figuring out in what way can we account for the behavior of the inductor? What way can we account for the behavior of the capacitor? And what way can we account for the behavior of a resistor? All of which, when they're subjected to an AC power supply. And what we see is that, in fact, the resistor pretty much doesn't mess with the phase. The current and voltage peak at the exact same time and trough at the exact same time and go to zero at the exact same time through a resistor. But for an inductor, we have Eli, so that the voltage leads the current in the inductor, and then we have ice, so the current leads the voltage in a capacitor. What does that mean? Well, that means when we go to solve a physics problem, for instance, a particular LRC circuit, then we have to deal with that, because, for instance, we're used to saying that, you know, if you put, say, 3 resistors in series, then the voltage across resistor 1, which we'll call V1, plus the voltage across resistor 2, which we'll call V2, plus the voltage across resistor 3, which we'll call V3, those should add up. V1 plus V2 plus V3 should add up to the total voltage V. That is not the case with these, because they're not necessarily all in phase. And in fact, you'll quite normally get voltage adding up to greater than the peak voltage or greater than the RMS voltage, whichever one you want to do. So what we're going to do now is use a phasor diagram to make some sense of how a circuit actually behaves. So what I'm going to do is I'm going to work a specific physics problem using a phasor diagram. And that particular physics problem is the following. So let's say, here's our example. We have a resistor R equals, let's say, 40.0 ohms, a inductor or an inductor, which might be a solenoid. L is going to be equal to, let's say, 50.0 millihenries, and a capacitor C is going to be equal to 24.0 microfarads in series. And they are connected to a, where's my calculator? To 170 volt AC source at a frequency of, let's say 600 hertz. Okay. What I want to know is, I would like to know the root mean square current. So what is IRMS? B, what are VRMS C, VRMS L, and VRMS R. I will say part C. Now you don't know exactly what I'm talking about here, but what is phi, the phase angle? And D, the power dissipated. Okay, so that's our question. What are those things? Now, how do we do such a thing? Well, what we do is we first make a little coordinate system. And to be honest with you, if you take a more advanced electronics course, you'll learn that actually what we're doing with these phasor diagrams is we're making a coordinate system where the y or vertical axis is the imaginary axis. So we're actually graphing imaginary numbers, in other words, and the horizontal axis is the real. So what we're looking at is basically instantaneous readings of the horizontal axis will give us instantaneous readings of the voltage or the current, depending on which one you're graphing. So in this case, what I'm going to do is I'm going to go ahead and draw exactly what this process looks like. This is called a phase diagram. And what it looks like right now is we're going to say this is X and say this is Y. And we're going to imagine for starters that there is a voltage given by V R0, which is I0 times R. So I'll first say this is my voltage. And this is V0 equals I0 times R. And for the record, that little current right there is basically I0. And that's really the current going through the resistor. That's the main thing to realize about that. That has nothing to do with the resistor, the current going through the capacitor, any of that sort of stuff. Now, what we also know is that the voltage across the inductor, V0L, is equal to I0 times XL, which is equal to I0 times omega L. And that's going to be ahead of the current. So what we're going to do now is draw another red vector. And this one's going to be VL0, which equals I0 times XL. That's how we fix it to make sure that it's 90 degrees ahead of the current and the capacitor, and the resistor and the current for the AC power source, of course. So it's 90 degrees ahead. And then we'll draw yet another red vector. And this vector is going to be behind the other one by 90 degrees. So this one will be VC0, which equals I0 times X sub C. And of course, we know that means VC0. I put the subscripts in different order on that last one by mistake, but that's okay. That's equal to I0 times XC, which is equal to I0 times 1 over omega C. Okay. Now, what's going to happen is this phasor here, these three red arrows are going to rotate around this axis with a frequency of F, which is also omega is 2 pi times F. So that can give you an idea of what it is. So at any point in time later, this coordinate system will still look the same, but the actual phasor is going to be in a different spot. So let me show you here. Okay, also looks pretty good. So what I'm going to do now is I'm going to draw that first phasor. That's my V0. Okay, and then 90 degrees ahead of that is VL0, and then 90 degrees behind that is VC0. So ultimately what you're going to do is you're going to add these things as if they're really vectors, and you can see that basically the sum of these would be about like this. So what we're going to get is, let's say, I'll use this dark blue color. We're going to get that particular value right there, which is the voltage through the resistor. Actually, I shouldn't say that one's the voltage through the resistor. Let me get rid of that. I'll just say this is sort of the net voltage that we're looking at. So I'll just call that V. But I think you can see what V is. V comes from basically you adding, are you subtracting from VL0, VC0, and therefore the difference is this little itty bitty quantity right here. And obviously if VL0 is larger, that's going to pull it ahead. If VC0 is small, larger, it's going to pull it back. But the main thing is this angle right here is omega at a time t. So at any time t, it's going to be there. But here's the weird part. This angle right here is going to be the phase angle. And that basically tells you the net effect of those particular parts. In other words, the inductor is going to tend to pull the phasor diagram ahead of the current through the resistor, and the capacitor is going to tend to lag it behind. The net effect is, in this case, assuming VL0 is larger than VC0, in this case, it's actually ahead by an angle phi. So that's really what's supposed to happen here. This quantity, actually, I should here. Let me clarify what this is. This quantity is in fact VR0, and this new quantity, the phasor, is really going to be our new, oops, wrong color, is going to be our new V0, and that's the wrong color too, but that's good enough. Okay, so what we're going to say is V0 is really going to be I times Z, and Z is a whole special thing now. This is called the impedance, but it also has units of ohms, but it's the net effect of all these things. So it's going to be I0 times C, which is in fact I0 times the square root of, in this case, you're going to say R squared plus XL, because XL tends to pull it ahead, minus XC, because XC tends to pull it behind. That's got to be after the minus sign. And I just did a bad job there, so I'm redoing it. And that will be squared like so. So this is actually how we get the net I0 peak to peak, if you are peak voltage, if you will. And of course, if you want to divide that by the square root of 2, you get the root mean square. You can also see that this is basically V0 squared is equal to I0 R0, or excuse me, I0 R squared plus omega L minus 1 over omega C squared. That's really what, left off the I0. Let me make this a little bigger. Let me kill this. Let me move this over here. Kill this. Put a square bracket right here. Make I0 right here. And put the exponent of 2 there. Okay, and you can also see from this that in fact phi would be equal to the inverse tangent of, obviously, this should be XL minus XC over R. Of course, you could also multiply through by I0, and you'd see it's basically this quantity that's in the square brackets, and then that quantity that's in the parentheses right above it would be in the bottom. So you can also do it that way. But these are the important results we'll need. We now have our data. So I can go ahead, and what I'm going to do is take this and copy this to the next page. Oops. Okay. I'm going to say copy. I'm going to go to the next page. I'm going to say paste. And I'm going to move this right here. So this is our problem that we're actually working. So now I just have to use those results. So in order for me to find the VRMS, I got to find V0, and then I got to find the impedance and that sort of thing. So let's do the solution. So VRMS is actually V0 over the square root of 2, which is actually I0 times the square root, times the square root of R squared plus XL minus XC squared over the square root of 2. Okay. So if I want the, and I think that's what I asked for, right? I asked that. So I said I0, we got I0 already. I0 is 170. Oops, I said that was supposed to be V0, and I ended up saying that was I0. Oopsie. Let's, I don't want that. I wanted, yeah, that's supposed to be V0. Sorry about that, guys. So right here, and I'm going to change it on the other page too. I don't know why I wrote that there, but I did. So there's V0, not I0. And I want IRMS. That's where, yeah, I did ask for that. What are VRMS? Okay, IRMS is what I did ask for. So that's cool. Now I'm just going to quickly shrink that, go back to the other page, erase this I0 to make sure that's correct. Put that to be V0. Obviously it's wrong because I had voltage next to it. So in order to do this, I obviously need the resistance, which I got, but I also need XL. So XL is equal to omega times L. Well, omega is basically 600 hertz times 2 pi f. So, or 600 hertz times 2 pi. So it'll be 2 pi times 600.0 hertz times the L, which we made the L 50.0 times 10 to the negative third henries. And now I'm going to pull out my calculator. I'm going to say 2 times 3.14159. It's actually, believe it or not, easier for me to do that than this to make this thing pull down to pi. So I said 2 times pi times 600 times 50 exponent negative 3. And that gives me 188.50. 188.50, and because that's a 5, I actually wrote 2 extra sig figs and that is ohms. Now I need XC. So this is actually a pretty high frequency. Remember, you're in your house, that frequency is usually 60 hertz. This is 10 times larger than that because it's 600. So in this case, this is 1 over omega C. So this would be fraction bar 2 pi times 600.0 hertz times the capacitance, which is 24.0 times 10 to the negative 6 farads. And I'll put my 1 over that. So I'm going to say 1 divided by parentheses 2 times 3.14159 times 600 times 24 e to the negative 6. Close parentheses. This one, in fact, gives me 11.052. Ohms. Again, I'm carrying another extra sig fig there because it was a 5, and I wanted to be clear as to whether I'd already rounded up or any of that kind of thing. So now I can finally say that Z, the impedance, which is equal to the square root of R squared plus XL minus XC squared, I can say that is equal to the square root of the resistance is 40.0 ohms. I'm going to square that. And in this case, the XL was much larger. This is 188.50 minus 11.052. Those units, by the way, are omega as well. I'll put them in that way. And then I got to take the square root of all that junk. So we'll start off with 188.50 minus 11.052. Obviously, I only am good to 1 sig fig on that, or 1 decimal place on that second thing. So, and I'm only good to 0 decimal places on that first thing. So 177.448 should really be rounded to 177, according to the sig fig rules. So I got 177, that's going to be squared. That only has 3 sig figs, plus 40 squared. Now 40 squared is going to be 4 times 4 is 16, but 10 times 10 is 100. So that's 1600. That should only be good to the nearest tens place. And 177 squared should only be good to, oh yeah, about the hundreds place. So it looks like we're going to get the square root of 33087.79 ohms squared. That's what's actually under there. But when I do 177.448 squared, that actually only gives me to the nearest hundreds. So really, this, and this are all insignificant digits. So I'm not supposed to be counting them, but that's okay because we get to take the square root and just round it to 3 sig figs. So I'm now going to take the square root of this, or the square root of 33087. 33087.7927. Got that. Square root of that is 181.90. So this is 181. That's terrible. 181.90. That's again two extra sig figs. I didn't need to write 2 that time. I just did out of habit. Okay. So now I'm finally in a position to write that V0 is equal to I0 times Z. So I'm going to do times 170. That's going to give me 30,923. which is really unreasonable. Volts. Ooh, there's the problem. I just did the wrong thing there. Yeah, that was very unreasonable. And the reason why is because I've unreasonably used the wrong thing. So yes, V0 is I0 times Z. We've got to actually calculate I0.
I have a question.
Yes.
What exactly is impedance?
Okay, so there's impedance and then there's reactance. Reactance is it's like resistance in that it has units of ohms. So it does tell us something about how much the voltage will drop across that particular item. So for instance, the voltage is going to drop across an inductor by an amount I0 times XL, which is the reactance. Similarly, the voltage across a capacitor will drop by I0 XC, which XC is the capacitive reactance. And in that sense, it's just another type of thing for resistance to give us an ohm-like law. But it also, because if you were taking this in a more advanced class, what they would call XL, they would actually say that's I times omega L. And then what they would call XC would be basically negative I over omega C, but that just adjusts the phase too. So it's useful for that. Now, the net effect is there's a little tendency to pull the voltage ahead of the input voltage. And that tendency is basically part of the, what you call what's the reactance, but also it's part of the impedance. So the impedance is basically the equivalent resistance thing that sort of takes into account not only resistance, but it also takes into account the capacitive reactance and the inductive reactance.
Okay, thank you.
I know that's not a very happy or good answer. I know that's not clear. I know that's not not the wonderful Shangri-La moment that you were hoping to bring some understanding. But what we've discovered is that when I go and measure, for instance, the voltage across a AC circuit across an inductor, you will get a VRMS if you, assuming that you're measuring it with a multimeter that measures RMS, you're going to get a VRMS that's consistent with the existence of this impedance. So at the end of the day, you can just say it's this way because evidently experiments said it was going to be that way. Now, what we do have is V0. So since we have V0, we can realize that I0 is going to be, in fact, oops, man, oh man. I know what I did. Remember I told you I'd written that 170 volts? What I was doing was really trying to make the peak, and that's okay. It's going to be V0. But your book does one like this, only they give you VRMS instead of V0. I'm giving you V0. So just know that that's the difference between this example and the example that your textbook gives, which I think is example 3011. Yes.
And to calculate V0 from VRMS, we just multiply by the square root of 2.
Well, you divide the I0 or the V0 by square root of 2.
Right, but to calculate V0.
Oh yeah, right, exactly.
VRMS.
Yeah, so that's in fact where I got the 170 from, is I basically took 120, which is roughly what wall voltage is, and multiplied it by the square root of 2, and that gave me 169.7. So yeah, that's exactly right. So now that I take this V0 and divide that, in fact, by Z, I'm going to do 170 divided by 181.90, giving extra sig figs, obviously. And that's, in fact, 0.93458. 934. And since that's a 5, I definitely need to add both digits there just to make sure everybody's on the right path here. So that's amps, and that means IRMS, which is I0 over the square root of 2. So IRMS is equal to, so this is part A, divide that by square root of 2. And that gives me 0.66 08 amps, or you can say it's 660.8 milliamps. So that's part A. Everybody follow that now? Okay, so we've got that. Now what we want to know is what is the RMS voltage across the actual resistor, across the actual capacitor, and across the actual inductor. What I'm going to do is, since we're using this V0, we really need a VRMS. And in fact, I should have, well, I'll go ahead and do it now. I'm going to say that VRMS is equal to V0 over the square root of 2. And I think you'll find that's 120. So 170 divided by square root of 2 gives me 120.2 volts. So that'll come in handy because we're obviously going to need it. So or actually we won't need it now, come think of it, but anyways, now we'll do start part B. So part B, we want to know VRMS. So VRMS across the inductor is IRMS times XL. So we know XL is 188.5, so I'm going to go 0.6608 times 181.5, 0.6608 amps times 188.50 ohms, and that's going to give us 124.56. Again, I just unluckily got another 5, so I had to carry both of those sig figs. So that's the VRMS across the inductor. So what this literally means is if you took our voltmeters that you've been using in lab, those little multimeters, the blue ones, that's what they measure when you put them on voltage AC. It's basically a little V, and then it's got like part of a little sine wave above it. That means it's used for measuring the voltage of AC. So when you put it on that setting, it's actually reporting RMS. So that would be the reading that your circuit would give if you actually set this circuit up and put the multimeter across the inductor. Now, putting the multimeter across the capacitor is going to be done the same way. It's IRMS times XC. Now this one will be a lot smaller because XC was like 11. So this will be teeny weeny, 0.66. I don't know why I used the phrase teeny weeny. I don't know that I've ever used it before. Except when I was a little kid, but anyways, so now XC is going to be 11052 ohms. So we're going to go 0.6608 times 11.052. That's going to give me 7.303 volts. So that's the RMS voltage across the capacitor. You can see already, since we did calculate VRMS, see, there was a reason to it. VRMS was 120.2. You can see already that just the voltage across the inductor is bigger than the RMS that the actual source is putting out. So we know they're not going to add up like the regular DC does. But now I'm going to say now I'm going to calculate VRMS for the resistor. So VRMS resistor is equal to IRMS times R, which equals 0.6608 amps times, now the resistor was 40, so this would be 40.0 ohms. So I get 26.4, and one extra sig fig before 3 volts. And that's the RMS voltage across the resistor. Any questions on that? So these are all part B. Part C, they want to know the phase angle. That's pretty easy to calculate. So the phase angle, remember, omega, or excuse me, phi, is the inverse tangent of XL minus XC over R, and the inverse tangent of XL over XC, that of course is 188.50 minus 11.052 minus 11.052, and all that will be divided by 40.0, and of course this is all in ohms. And actually, let me fix this. That did not turn out too well. I can do a parenthesis around here and put an ohms there and an ohms there, and then that way it at least looks like we're dealing with the units. But you can see the units are actually going to cancel out. So I'm going to say 188.5 minus 11.052 gives me 177.448, but that should really only be to the ones place. So that's okay. We do get 3 sig figs. Now I'm going to divide that by 40. That should give us 3 sig figs. So I'm getting that the phi is equal to the inverse tangent of 4.436. That has no units. So I'm going to say second function tangent inverse, second function answer. And that gives me 77.29. This is a really big phase angle. 77.296. This is a 9. I really should put 2 on there because otherwise I'd make it bigger. So it's 77.296 degrees is what the phase angle is, and that's part C. Any questions on that part? So if you actually looked at the voltage, you put the voltage on, say, if you actually looked at it through an oscilloscope, you would see the voltage through the capacitor, and that would just look fine. But the actual voltage, say, coming from the power supply versus the actual voltage going through the circuit, you'd see that it's actually ahead by almost 90 degrees. In fact, 77.3 degrees roughly. So that's really what that's showing. But the important thing is once you have that phase angle, then you can make use of other stuff. You can, for instance, realize that the power formula has to take into account that the peak of the voltage and the peak of the current are not occurring at the same time. So what would normally be P equals I times V, in this situation, you can't say that because you need the component of I, say, or component of V, say, that's parallel to the other. Specifically in the real part of that graph, that phasor diagram, what we're looking at is the projection of that new vector onto the x-axis. So that is power is equal to IRMS, which is an equation you should have on your equation sheet, times VRMS times cosine of phi. That's how you're actually going to calculate it. Now let's look back at that phasor diagram real quick. You can see on this phasor diagram that when we take the cosine of phi, see that takes that dark blue vector, that takes it and finds the component that's parallel to VR0. That's why that's there. Go ahead, Michael, you got a question?
Yeah, would it be possible to do IRMS squared times the impedance for power?
No, I don't recall that working that way. I'm trying to remember any other versions of it. Oh yeah. So you can do I squared Z cosine theta, but not I squared Z. I just pulled back up to the book to look for some of their results. So some of the other ways you can do it, I'll write here as well, just to let you know. So that's one version. Another version is we could write IRMS squared times the actual impedance. But if we're going to do the actual impedance, we still have to include the cosine phi. What I used was the IRMS times VRMS times cosine phi. So that's basically it. You could, in principle, I guess, use I squared times R, because R really is going to give you the Z times cosine theta. Yeah, that has to. So that would work as well. I'm trying to see if your book has that. Yes, your book does have that. It doesn't list it as a numbered equation, though. It says it on right above equation 30-30. So I'll say look above equation 30-30. And you'll see that that's also a viable option. I'm going to use that first one. Is that was that a good enough answer, Michael, or do you want to talk about something else or ask something else?
No, I'm good.
Okay. 0.6608, if I recall, is the current. This is your lab teacher. Let me answer this real quick since it's your lab teacher. Hi, Ms. Raskovic. How's it going? Okay. I will. Okay, I will tell them don't touch any of the lab equipment, but you might be a few minutes late. Okay, no problem. Drive safely. Bye-bye. Hey everybody, I was right. It was wise for me to do that because she won't let you know she's been trapped in traffic and she's possibly going to be late. But she just wants you not to try to touch any of the lab equipment. If someone's left the door open for you, you're welcome to go in. Just don't touch the lab equipment because there's an element that might not be so good to do. So I suspect she might have something that's potentially dangerous. So she just don't want to do that. Want you to do that. All right, so I've already gotten the IRMS. Now I got to get the VRMS, which for me was 120.2 volts, which is 1 extra sig fig. And then I'm going to take the cosine of 77.296 degrees. And that's going to give me the power. So I'm going to say 0.6608 times 120.2 times, now I'm going to do cosine of 77.296, close cosine. So I've got 17.47 watts. So that's the average power dissipated. And I'll go back to boxing that off with a red box. Any questions on that? So that's the main thing that I wanted to make sure you knew about. Your book goes on, it talks about three-phase circuits, which is basically what we use here in America. I think I might have told you at one time errantly that they were 60 degrees off. I was misremembering. They're actually 120 degrees off. So basically you have V equals, if you want to talk about voltage or if you want to talk about current, you could do either one. But I'm going to say V equals V0 times cosine omega t. And then you've got another one that's V equals V0 or V2 equals V0 times, notice it's the same peak, times cosine of omega t plus 120 degrees. And then the third one is V3 equals V0 times cosine omega t plus 240. So that's what the triphasic voltage is. And because of that, you can take the positive peak of, say, the first one and then compare it with one of the negative peaks of the other one. They'll actually line up enough that you can see that the net effect is there's a 240 volt difference between the peak and the negative peak. That gives you 240, which is what we use in stoves, what we use in dryers as well, but not washing machines. Okay. So it's good. It's a good thing to read. I definitely would like you to read all of this chapter, but I will tell you that resonance in AC circuits, there might be a concept question about it in the concept homeworks, but I'm not intending to ask you any questions on midterms or final exams or any online tests. My attempt is not to give you any questions on resonance, impedance matching, or three-phase circuits. That being said, I absolutely consider LRC circuits fair game. I consider LR circuits fair game, RC circuits fair game. Basically, all the stuff that we did in this chapter up through 30-8 is fair game. So any questions on that? So up through section 30-8 is what you're responsible for. I'm going to write that on that thing. So B, responsible. Well, we'll put a P on that. For sections 30-1 to 30-8. For tests and exams, midterm / final. Of course, we've already had a midterm, so obviously that's not the point. But anyways, so I did write that down. Did anybody have any other questions on any of this stuff? Your author does a good job telling about what you can do. So for instance, we see that really high frequency stuff can't make it through a inductor. So if you want to, for instance, connect a stereo output, so the actual sound output from a stereo, if you want to connect that to a woofer, that's supposed to be all low frequency stuff. So you could actually put on the wire in between the stereo and the woofer, you could actually put a solenoid, which is basically an inductor, in line with it, and that would stop all the highest frequency stuff getting in, and your woofer would play just the lower frequency stuff, which is what a woofer is supposed to do. Similarly, you could run a wire through an inductor and then to ground between the stereo and the actual tweeter. So as the input signal comes out of the back of the stereo, you would continue that wire straight on to the tweeter, but you would branch that wire off and send a certain amount of that voltage through the inductor to ground. And what that would do is then force all the low frequency stuff to run to ground, so you'd only get the highest frequency stuff coming to your tweeter, which is, again, what you want from your tweeter. So any questions on that? All right, so I'm going to tell you something else now. We're going to go ahead and start into chapter 31. So let me flip pages, and I'm going to say chapter 31. Now, chapter 31 is about Maxwell's equations. And I'll start off by telling you that this, of course, the closed integral of E dot dA is equal to Q over epsilon naught. That's Gauss's law. But there turns out to be a similar equation, which you might not necessarily get. But right here, what I want you to understand is that left-hand side is the flux. We've talked about flux before. We talked about it again with Faraday's law. In fact, the electrical flux and the magnetic flux. But we're going to now talk about electric flux as well. But the main thing is when we were doing diagrams of electric fields, what we realized, or hopefully what you realized, was that electric field lines, electric field vectors start on a positive charge. In other words, there's a positive charge in space and the arrow leaves that and runs into a negative charge. And then that's when the line stops. That's the way electric fields behave. They start on positive voltages or positive charges specifically, and then end on negative charges. And that's what this equation is showing. Well, magnetic fields, if you actually looked at a bar magnet, you would see the magnetic field lines come out of the north end. Remember, I made the joke that it's like old people, they leave the north and go into the south. So the actual bar magnet would have a magnetic field line coming out of the north end, and it would actually loop back around and then come in the south end. But here's the weird thing. If you are actually capable of doing it, you would find that the line, the magnetic field line, and therefore vector, continues right through the iron that you use to make the bar magnet. In fact, that's the nature of magnetic fields. They always loop. They never just terminate. And if they do, it's just a transient thing that just happened because of some freak of nature, which is what goes on outside the edge of the photosphere of the sun all the time. You'll see huge loops that are mimicking magnetic field lines and huge flames and fire tornadoes going around those. But every now and then one of those will just break. That isn't the existence of a monopole. That's just a inability of space to support the magnetic field, so the magnetic field died. So because of that, what we've learned is that evidently there's no such thing as a free wheeling north pole of a magnet or a freewheeling south pole of a magnet. And just like we showed you when we first covered magnetism, it turns out that when you cut a magnet in half, you end up making two magnets, each of which have a north pole and a south pole. And if you cut it too small, you're eventually just going to get to the point where it won't be a magnet at all, but it'll never be a separate north pole and a south pole. So it turns out the equation for Gauss's law for the magnetic field turns out to be just the closed integral of B dot dA is equal to 0. Okay, notice I left off the enclosed ENC subscript. That's just to save some room. Now, there's also another equation we learned, and that is, of course, Faraday's law. And Faraday's law told us that the closed integral of E dot dl, now you might not remember it this way. We just said the EMF is equal to the negative time derivative of the magnetic flux, and we might have put an N in front of it in case there was many, many turns. But the main thing is we get d by dt of the magnetic flux. So that's Faraday's law. And we have a similar structure, which is the closed integral of B dot dl is equal to mu 0 I. Okay. And of course, I'm leaving off the ENC subscript on the I this time as well. This is called Ampere's law, but it's not complete. There's something missing that symmetry told us about, but Maxwell had other reasons as well for thinking it needed to be fixed. And ultimately, Maxwell did fix it. So I just did a horrible job writing Ampere's. Maxwell did fix it, and that's what we'll cover next time because we're running out of time. But Ampere's law is this one, but like I said, it's incomplete. Okay, so you definitely have plenty of material to go on 30. Chapter 30, you actually had enough material before today as well. Just that last part wasn't very kosher. So you can expect another test coming up soon, maybe 2 coming up soon to catch us back up. As I said, this is starting chapter 31. I'm going to convert these differential equations really quickly next time, and I'm going to knock out electromagnetic radiation, the EM spectrum, the Poynting vector. I'm going to derive a field equation, or excuse me, wave equation for the electric and magnetic fields. So that'll all be done next time. You guys are free to go. Remember, our Maria has just called me and said she's going to running late, but please don't touch the equipment when you get into the lab. Have a good one, everybody. I will see you next time.
Thank you, you too.
Thank you.
And is chapter 30 part 1 and part 2 due tomorrow?
Yes, they were due tomorrow. I might, since I ended up covering some of that last material today, I'll probably put the second one. Maybe I'll make that due Friday or something like that, or Saturday or Sunday or something, just to give you all a little bit more time. But definitely get one of them knocked out at least.
Okay.
In fact, I'll do that right now because I can. Anybody else have any questions?
I'd sent a message on Canvas about the work we do in class here. I think somewhere it said you like put it on your Google Drives. Is that right?
Yes. Yeah. If you look at the, it's like the second module in Canvas, you'll see a link to my Google Drive, and that's supposed to be a permission. So you should just be able to click on it. And because you have that link, it should take you in there without any permission. Sometimes for some reason, Google asks you to, for permission, or ask me for permission. So if that happens, I'll respond to it as soon as I can, or as soon as I see it.
Yeah, when I sent the message, that's what I tried to do, and it said I didn't have permission to access it.
Okay, and this is Warlittner. Yeah, gotcha. I'll make sure I'll look for that email and change that for you guys.
Okay. Where can I find your email? Because I looked at syllabus and all it has is the actual course dates on it.
Oh, so my email's not on there?
I didn't see it on there.
Okay, well, let me stop recording for a second. It's best not to put such things out in the interwebs.